Assalamu alaikum. I am Isam Nafis Ahmed. I have completed my undergrad from Military Institute of Science and Technology in Computer Science and Engineering in July 2025. Currently, I am working as a research assistant in Military Institute of Science and Technology. Also, I have prior experience in software engineering. I have worked for the Bangladesh military. Also, I have completed my industrial training from Base Station 23. From the very beginning of my academic life, I have devoted myself in research. Currently, I have authored 2 journal articles and 5 conference papers. That's all about myself. Now I'm going to move on to our today's question answer session. So our first question is outlining an algorithm for finding a minimum spanning tree in a distributed system. Follow up is in what real world ML scenario would you use MSTs? So there are multiple algorithms. So among them, I have choose GHS. This is Gallagher Hamlet and Spira algorithm. So before digging into that algorithm, I'm going to talk about some basics for better understanding. Uh, let's see this example in this image. So this is an undirected graph. So the question may arise, what is spanning tree? So spanning tree is basically is a tree inside an undirected graph where we have actually connected all the nodes using the edges, and these edges will have some weights. So this is a spanning tree. And what is minimum spanning tree then? Then minimum spanning tree is the tree which has the most, which has the smallest possible total edge weight. That's it. For here you can see it is 4 plus 1 plus 2, it is 7. And in the spanning tree here you can see it is 4 plus 5 plus 2, it is 11. So this is the smallest one. So we are calling this as a minimum spanning tree. So in the problem we have mentioned here, it has said about the distributed system. So and now I'm going to talk about something about why I haven't chosen the popular models like Pim's algorithm or Kuskal algorithms. So Pim's algorithms, Kuskal algorithms are very good, but they actually not good for a distributed system because they are difficult to apply in these scenarios. The two main reasons are both algorithms processing one node or vertex at a time, and also they require process to know the state of the whole graph. So it's not always possible to know the state of the whole graph at that time. So how this there so these problems are mitigated using GSS algorithm. I will go for there, but before going there, I'm going to talk about some basics. For example, what is fragment, what is MOE. So if we see this graph, so in this graph, during building the MST minimum spanning tree, we actually getting a subset of nodes. These subsets of nodes are called fragment. We can also call this dotted part as a fragment. So then what is MOE? So MOE is nothing but that if you see that what are the outgoing edges for this node, the outgoing edges is this one, then this one, this, and this. Among these marked edges, which one has the lowest weight? So if you see, the 9 has the lowest weight. So we are calling this one as minimum outgoing edge, MOE. So what is the significance of MOE? The significance of MOE is that MOEs are used to connect the fragments. Our main goal is to build an a minimum spanning tree using joining or merging these fragments, and this task is done using the minimum outgoing edges. We'll see it later. So yeah, there's another concept called level. We are going to use this level to actually merge this and get the value of the level of the fragments. So initially all these nodes uh, are are fragments. So we will for all the nodes the level will be 0 at the initialization. So but after we process further, there will be two cases. Case one, which is actually says that if we see this example, uh, this is fragment F, which is currently at level 1, and fragment F prime is level 1. Both of the fragments are at level 1. So when we are going to merge this, the new fragment will be L plus 1, which is actually 2. This is the case 1. Then we are going for the case 2. So in case 2, if they are not same, that means that they are in different levels. For example, here F is at level 0 and this one is F level 1. So when we are going to merge this, we'll be getting uh, what level 1. But how? It's because of the max L of LO and L1, which means among these two, which one has the maximum level. We are going to put that value to our new fragment level, that is level 1. Now let's understand the GS algorithm with an example. Suppose we are setting up a wireless sensor network, WSN, in an agricultural field. So there will be multiple sensors like temperature sensor, humidity sensors, soil sensors, light intensity, and many more. In the real world scenario, it will look like this. This is a very uh, complicated and complex scenario where actually there are multiple sensors and they are passing data from here to there, and this is very much we can actually see from looking at this. We can actually see tell that there are so many redundancies here. So this is going to be a very hard job for machine learning models to actually, going to train, because we're going to get a lot of redundant features, and training these features, the model, it will not only be costly in in terms of cost time, also it will be a reason for overfitting. So because they are going to memorize the answer, so that's not a good thing to do. So so our goal is basically is that we're going to select some representative sensor, because we actually don't need so many sensors. So for example, there are 10 temperature sensors, so I'm going to choose only one temperature sensor for a representative. Then we're also going to be make an efficient combination network. It's very common, because actually we're reducing the sensor, so the transmission cost will also be low. So how this GSS algorithm works? First of all, we have to assign the weights of the edges. I am in this scenario, I am telling these edges as short edge and long edge. What is short edge? So if the sensors are giving similar readings, then we are calling it as high correlation. Why? This is a temperature sensor 1, this is a temperature sensor 2. Both of them is giving is 25 degrees Celsius. Both of the data is almost similar readings. So I will tell that they have high correlation. That's why they are short edge. The edge value is will be short. Now, what is long edge? Long edge is if the reading is totally different. Like humidity sensor is giving in different value, and temperature sensor is giving different value. It's totally different sensors with different readings. So I'm going to call this as long edge. So we're going to run this GSS algorithm. What GSS algorithm will do? It will start the sensor as its own fragment, because we are considering each and every sensor as a node, or we can call it vertex. So in in this scenario, we will have uh, initially we will have a lot of sensors, and all the sensors are going to be a fragment. Then we are going to use MOE for connecting these fragments. And after that, we will be getting only one minimum. We are getting a one spanning tree. That is going to be a minimum spanning tree with a minimum total edge width. So this is how we are going to be. This is how we actually build a MST in a distributed way. So how this MST are actually used for feature selection. So it's a very common thing is that in previously have already told that long and short is. So if I actually remove this weakly correlated part, then our task is done. So we are going to cut out the long edges because they have no similarities, and we are going to select one representative sensor. Or I already told that there are 10 temperature sensors. I'm going to select only one temperature sensor for representative. So that's how I am actually choosing the feature, or in a sense, I am selecting a representative sensor. So what's our outcome? Lower energy uses, efficient routing. And in machine learning our tasks, we can actually do a very efficient predicting of soil quality, detecting crop diseases, forecasting irrigation needs. That's all. Then moves on to the question number two. What it says: given a large stream of user interaction, design a data structure for a login, read some queries and updates, supporting both exact and approximate application for downstream feature generators. Follow how would you parallelize updates for distributed feature stores. So I have this is a large problem actually. So I have divided this problem into some sub problems, and I'm going to solve these sub problems, and ultimately I'm going to get a solution that is going to be fulfill all the problems. So in the first sub problem, I have given focus on the exact aggregation of this down to feature generation. Then the second sub problem I have focused on the approximate aggregation, and lastly, I have focused on the distributed or parallel design. So for problems for subproblem one, what solution I came up with is that I'm going to use a Fenwick tree or binary index tree. So why? Because if I go to this table, so here actually I can see that the starter insertion time complexity is about log n time in the worst case, and the space complexity is order of 9. So that's fantastic thing, because we'll know why it's fantastic in future in further. So a common question may arise why I have chosen BIT over segment tree, because the same time complexity is also being achieved by the segment tree. So why I have chosen BIT? There are two reasons. First of all, I'm a lazy person, so I I actually look for the easy implementation techniques. So BIT is a very easy to implemented code. So if I see here this part of code, then this part of code, this is very easy to implement. And whereas in segment tree, I need to write a lot of code. So yeah, I will definitely going to I'm going to ignore that one. Another big reason is the space efficiency. We know in segment tree we actually need 4n spaces. N is at the array, size of the array, and but in the BIT we actually need of n space, means the size of the array, because we are actually using an additional array t, we will see later in this image, which is actually giving us these values. So it is more efficient in the terms of space. So I have chosen BIT for exact aggregation. Now, how this actually works, this Fenwick tree or BIT, it is very easy. Uh, for 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 this, I am going to explain this example. A is a frequency array where one is representing the. I am giving an example. For one is means customer ID, customer number one, and what is the value of what the value means? That value means that one has 5 interactions, or five interactions. Two has 2 interactions. This is a frequency array. That's why we need prefix sums. So how we get the prefix sums? So if we actually convert these indexes into binary, we'll see at the less significant bit, we look for the bit 1. So here is the bit 1, then here is the bit 1. Actually we can see this mark things here, one, this one, and this one, and this one. We are going to give this value as it is. Like here is 5, I will give it 5. Here is 9, I will give it 9. Like this, I will give all the values. Secondly, I will shift it 1 bit again. I will count to this one, second bit. Then I will also look for 1. Then I will going to calculate this sum. Then for this, I want to calculate this sum. Then this one, and then this one. Then I'll putting this value like 5 plus 2 is 7. Then 5 plus 20 is 25. Like this I'm going to put, and so on it will go on, and I am going to put these values. Ultimately I'll get a array T is uh, actually is a tree. It is getting the values of the tree, and this tree actually will help me to get the prefix. How? This is an pseudocode. Initially, the sum is we are taking sum as it is a variable initialization. Then, what we're actually doing is that we're calculating sum t of I is we're actually adding the values. So here, this is the significant part. We're actually flipping the last set bit. Let's go for an example. For actually, there's a function called sum of 7. So 7 means 00111. So we're going to flip this less significant bit. For here we're getting this one is as it is. Then if I flip this bit, it will be 0. Then I will be flipping this bit, I'll be getting this. That means T7, T6, and T4. If I look into array, T7 means 10. Then T6 means 25, and T4 means 30. So after summing this, I will get 48. This is very easy technique. That's a very easy way to do this. And if I need a range sum, for example, sum of, sorry for the handwriting, sum of I comma j, what will I do? It's a very easy thing. Sum I minus sum j minus 1. That's how I'm going to get the range sum. I'm just I'm just subtracting the values. That's how you can get the sum. And if you look into this, it is actually doing in order of log n. I'm sorry for my handwriting. I don't have the mouse pad right now. Order of log n. Similarly, the add function, or you can call it as update function, it is actually happening the same way. Just initially we are actually doing the negative task here. Now currently we are doing a positive one because the last we went to set the last bit. So if we look into this, at 4 comma 10, 4 comma 10 means at the position of 4, like here, I'm going to add 10. So sorry, this is the resulted one, so I'm going to look at the previous one. So at 4 it is actually 13. So I'm going to add a 10, value of 10 here. So after adding 10, it will be 13 plus 10 is 23. Similarly, I will go one bit further and I will be setting this bit. Then I will add the values. For example, this is actually 8. So 8 position, if I look at the 8 position here, 8 position was 41. 41 plus 10, that will be 51. That's how actually I'm updating the values step by step. And after shifting one bit more, I'll be getting 16. But 16 is actually out of range because of my size of the array is 15, so it is out of range. So the loop will hold, and I'm updating my tree in an order of log n time. Now for the sub problem 2, I have chosen count mean sketch because count means CM sketch actually used for the approximate aggregation. And how it works, because in CM sketch we're actually using the sublinear space. What is sublinear space? We actually have a fixed amount of space, but the stream of data is infinite. That means there will be millions of data. So getting a frequency array or frequency values, or the what would yes frequency at values is not easy task for this stream of data. So and especially for this limited space, because we actually don't have that much of space. So we are going to use this kind of table. We can call it matrix also. So what we are going to use, we are going to hash functions, and there will be initially all the values will be 0. I have already given an example here. So this is the stream A, B, something like this, and I have already given the values of the hash function. For A, the hash, if I give A into h1 hash function, the output will be 1. Then if I give A to h2 hash function, the output will be 6, and so on. So ultimately, what happens is that I'm going to count these values. For example, if I go here, I getting 1, so I will be setting this bit as 1. Then H2 A6. So I in the sixth position, H2 and sixth position I will be updating this as 1. Then H3A at the 3 position there will be an 1, and again at the 1 position there will be an 1 for the each here. Similarly, it will go on for here, this one, this one, this one. There's another A, there's another A. So we can actually tell 1 plus 1 is 2 plus 3, 4. That will be 4. So here we can see actually updating these values will actually come up with this 2D array. So if we look at into this, we actually have done the count part. Here is the count part. Now, what is the mean part? If we look and if we actually looking for the value of a, the frequency of a, actually how many interaction a has made, if I clear the question. So how will I calculate that? I'll look into the this 2D array. That for a I can see I have 4 for position 1. For position 1 there's 4, so I'll be writing 4. Then position 6 there is 3, so comma 3. Then position 3, then position 3 there is also a 3, then I'll comma giving 3. Then at position 1 there is also 4, so I'm getting 4 values. So what does mean means? Mean means take the minimum value. So among these, which is on the minimum? Obviously 3 is the minimum, right? 3 is the minimum value. So the count of a is actually 3. So let's look into this stream. How many A's are there? 1, 2, and 3. Yes, it actually matches. I am not telling that it is always be matching this like this, but it will give a approximate value. Because why it is called not giving exact value? Because it is a compression technique. When we actually compress data, we actually miss some valuable information, and for this reason we actually going to miss some count, but it doesn't matter because this is an easy example. There is 3, but in the real world there will be millions of interactions for a single person. But for me, person like me who actually uses Facebook for 3 to 4 hours, actually doing a lot of interactions. So for me, if they give me interaction of how many interactions I have done, if in the case it will be 2655 in the exact value, but if the system will give the output that I have made around approximate 200 600 2600 interactions. So I'm okay with that. That 55 doesn't matter to me right now. This is actually saving the space. Actually, this is a very good way to solve the space complexity problem. So here is I'm giving that Fenwick trick. If I want reset or hot update, then I'm going to use Fenwick. Otherwise, I'm going to use count min sketch. Okay, the subproblem 3. Subproblem 3 means that I'm actually one parallel system. I'll be what will what. Oh, let's go to the exam question again. I have forgotten it. The question said that parallelize updates for the distributed feature store. So I actually want to store the features so in a parallel way. So how can I do that? I can do it by shading. Shading is a technique where actually we are dividing the users. For example, shade one I'm going to use for 1 to 10 million users. In shade 2 I'm going to use 10 to 20 million users. 20 million users, and for shade in I'm going to use some like that. I'm going to use something. So this is how actually I'm dividing the dividing it into some groups so that I can easily go into go into that group and actually update the value. For example, my interactions are currently at shared 2. Okay, shared 2 I'm currently at this position. So for updating my interaction, do I need to go with shared 1 or any other shared? I actually don't need to go. I'll go to the shared 2 and update my value. This is the technique where actually I can do parallels. So what the chat result give, bandwidth ransom and the sketch estimate ransom, because I am actually proposing, because the question actually said to be design and data structure. So I have designed a hybrid aggregator. So in the hybrid aggregator, I'm using Fenwick tree and count mean sketch. So the sum will be Fenwick sum and the sketch estimate sum. In summary, Fenwick tree is for exact, count means for exprove, and routing logic is the this one actually. It is for the direct update to the right structure. As I said, I'm currently at this position, so I need to update this one, not other one. So this happens in order of one because it is very easy, because I already have the user ID. I just need to go there and just update the value. So it is going to be in order one. Approximate also in order one, because I have already got the updated value. So I'm going to go there and take that value. Then the exact, for the exact I have already shown it is in order of log n time. So that's how I can achieve the, as the question said. Let's go to the next question. It is question number 3. I am very short of time. It is 11:48 p.m. and 12 a.m. the time I'm going to be in. So I'm going to be very fast. Uh, you are tasked with designing an ML model cache. Explain how a split tree helps optimize access pattern and what's the trade-off are compared to LRU caches. Follow up. When would you playing harm latency in serving prediction? Okay, very easy question. In machine learning models, actually, what we do is that. In this question, actually what they have told me to do is to quickly find and return the requested model, adjust automatically change access patterns, and use a limited modification. In short term, we are actually using a lot of machine learning models. So uh, we actually need a system where we actually going to call these machine learning models in a very efficient way, because if I ask for a machine learning model and it takes a lot of time to come, that doesn't work like that. So what I'm going to use, I'm going to use a Splatty. It already told me to use a Splatty. So Splatty is, what is Splatty? Splatty is a tree, obviously, that actually uses the rotation technique to keep the recent used node or machine learning model to be at the root. Very simple. The values, the recently used or the most used models will be closer to the root node. So there are two ways. Zigzag. Zigzag means left rotate. If I rotate for x, if I left rotate one time, it will look like this. And if I left rotate one more time, then x will be the root. This is zigzag. This is also called zigzag. What zigzag is actually, it is a right rotate and left rotate. So for x, I'm going to use a right rotate. Then that's why it is going here. Now I'm going to do a left rotate. That means I'm going to rotate it like this. Sorry, the different camera angles. So I will getting this at root. This is a zigzag. So searching, insertion, deletion, all of these are happening very easy, in an easy manner. If there is a value I want to search is 39, then it will come up and it will be at the root level. If the value doesn't exist, then the parent of this value, or that means 44, will come up in the root level. In the insertion, if I want to add a value for 51, I want to add 51 at the root level. I want to add the 51 value in this tree actually. So it will come up like this and at the root position. Similarly, if I delete the position, delete 39, so 44, the parent of this deleted node will come up to the root. That's how actually it works. And the question is, what is the trade-off between LRU and splitting? So frequently access model move to the top automatically, but LRU, it keeps only the most recently used models. There's a significant difference, because uh, we actually will see in the adaptability, it adapts both frequency and recency use, because how many times I'm using that machine learning model is one thing, and what machine learning model I have recently used is another thing. So it actually adapts the both information, because how much many time I'm using that, it will always be closer to the root node. And if I use in recent time, that means it will itself become a root node. But in the LRU, it doesn't matter of the how many times you use. It only takes care about what node or what machine learning model I have used in recent times. That will be the main concern. So workflows where some models are used much more often. For example, I am more interested in computer vision, so I use a lot of models for the computer vision models. So I don't need models of, for example, what for okay, I'll leave this example. I am not going to take that example because it will create a lot of problems for me. Systems that need fixed and predictable latency. Okay, uh, I if the system is it is like that I am using every model in a uniform matter like this. For computer vision, I'm using this model. I'm also using this model for large language model. I'm also using this for forecasting. So I'm a programmer who is actually using all of this model very frequently. So I'm going to use LRU for this case because LRU needs order of one time. But if I do if I use Splay tree, then it is not going to be an efficient way because I am using all of these models. So which one will be the most close to the root node? If everything comes to the root node, it is taking actually an additional time of log n. This is going to be a headache for the one users. So that in that case, we are not going to use a Splay tree. We are going for the LRU. So we should use Splay tree if particular there are some particular models that are used most. Then then it makes sense to use a Splay tree. So here I have actually mentioned these things. In conclusion, I have already said that in a uniform workload, Splay tree doesn't do good. So LRU should be a good choice. But in a sense, if we use some particular models much more, then Splay is a good option because it will take a less time than that. Then question number four. Oh, I am running out of time. Question number four: build a system to support efficient merging and querying of connected user components in a social graph as edges are added or deleted for clustering in ML. Follow how does union by rank and path compression speed up large scale ML graph operations. Let's see. Mm, the problem actually says that we are actually using a social graph where we are um, people are the people are the nodes and friendship and connections are the edges. So quickly tell if two user connected group user into cluster, we are going to cluster the users, handle the edges being added or deleted at the same at all the time. So how I'm going to build the system? First of all, I would like to build the input system. I'm going to make a I'm going to send the event every time because whenever one connection or disconnection is happening, I am going to send an event like add edge between A and B, remove edge between B and C. This is important because these informations actually helps us to safely put data in a keyword database like Kafka. Kafka is a open source software where actually we store the stream of data for this event based information. Then graph storage, we keep a big list of who's connected to whom. We think of it like A connected to BC, B is connected to AD. It's like Facebook friends. So like this, we are actually maintaining it using a address list. Union find disjoint unions. What are these? So if we look at this, there are two trees actually. You can see this is tree one, this is tree two, and here the yellow part recalls that sorry recalls not recalls it tells us that this one is the root node. This means this is the representative of this tree or leader of this tree. here is the 5 is the leader of this tree. So there are two leaders. So what there are two, what will you do? We will have actually two operation, find x and union ab. Union ab is first of all I'm going to tell what is find x. For example, if I tell what is find x, if I tell what is find 4, what is find 4? So find 4 tells us who is the representative of 4. So 4 asks 3, who is my representative? 3 asks 0, who is my representative? 0 asks itself, who is my representative? And 0 answers, yay, I am the representative of myself. So this is how actually this find value works. And if I come to the union, yes, in the union time we actually going to merge these two tree. So how you do that? It's a, we actually know what is very easy. We are taking the small thing and going to merge it with a large thing. But this is a very easy task. So we are going to take this small tree because this only have two nodes, two elements. So we are going to take this to this tree. This is our first concept, that we are taking the small tree into a larger tree. This is how union works. And after union, we will get something like this. And the question is, what thing there can be if we do union like union 3 comma 4, will it be union? The question is no, it will not going to be an union because they both are currently in the same tree, right? So what we are going to check is the parent find 2 and find 1, in this case union 1 comma 2. So find 2 will give me value of 5 because the representative of 2 is actually 5 and the representative of 1 actually 0. So it is 0. So 5 is not equal to 0. That means they are totally different trees. So I can merge them or I can union them. So after unioning, I'm going to get this. This is called union by rank. I'm mentioning it union by rank because I'm doing this in a rank fashion. Now, what is the same thing I would tell is what is path compression. And if we look at this, this is a this tree actually takes a lot of it will take a time of as it is a tree, then the height will be log n. So yeah, the time complexity will be order of log n. So I can make it more efficient because I don't need to make this tree like this. I can actually make it like 0, then 0 is connected to 3, then it will be 1, and there is connected by 4. And if I call find function now, it will give a value. If I put find function now, it will give my result in instance that yes, 0 is my leader, 0 is my representative. This is called path compression. I am actually connecting the nodes directly with the root node. This is helping me to get the parent in a very instance matter. So yeah, using an union by rank and path option together, actually it is going to give me a very efficient output. And lastly, the question asks, yes, I have already said that the rank and path compression speed up the large scale ML graph operation. Yes. So how it works, and last part I have already said. Each user's component size, connections, and group ID can be features. It helps find communities, influencer, and bot groups. You can train models to detect suspicious interesting clusters. I have taken this information actually from the Google, so this is not from my writing. Uh, but yeah, there's a important thing that I have missed is that uh, when we actually want to delete, the splitting operation is not such an easy thing for the union find of data structure. So how can we do that? There's a two ways to do. That's the easy way is that just mark the deleted edges and rebuild everything few up. after few hours. This is the easy way to do, but it is not an efficient way. There is another efficient way, that is advanced transform. It is called, if I use a Euler to trees. This is, I have already given a link to this. I'm not going to explain it here because it already I am out of my time. So Euler two trees actually helps us to split the data so that I can delete these connections and get it in very efficient manner. So all of this I have already told. I have actually, I'm really sorry that I couldn't speak much more about this information. I was very interested, and I am actually very passionate about machine learning models and everything. I've been working, as I said, I'm working for um, last 4 to 5 years in this field. So I'm very passionate about this. I couldn't make it because I was ill. Last few days I was ill, so I couldn't make this preparation. I have only taken 1 to 2 days to make this information to present something. I am very looking forward for this post, and I hopeful that I have able to make you understand what I have said, and I believe that um, I can do much better than this. And thank you for listening. And yeah, tata.